Lama Sejahtera Middle and Name. My name is Tamifang as a group leader for Group D, and our group member have Lumano Hakim, Aina Zukrina, and Sitino Anissa. Today, our group would like to present the Laminar parallel flow over the flat plane by computational fluid dynamics. Next, this is our task allocation for each member.
Introduction. A basic problem in computational fluid dynamics CFD that is used as a standard for evaluating numerical techniques and comprehending flow behavior is the simulations of laminar flow across a flat plate. The formations of a boundary layers, a region close to the plate where viscous effect occur, and the flow change from the no-slip condition at the surface to the free stream condition distant from the plate is highlighted by this classical problem, which has its roots in the Blasius boundary layer theory. The geometry, simplicity, and the availability of analytical solutions make it a perfect example for evaluating CFD algorithm and solvers. Next, theory. Blasius solution is a classical solution to the boundary layers equations for laminar flow over a flat plate. The Blasius equation is solved numerically to obtain the velocity profile Uy within the boundary layers. The velocity at any point is expressed as U equal to U inverse function of mu, where inverse function of mu is the dimensionless velocity profile. Skin friction coefficient Cf is a dimensionless quantity used to quantify the wall shear stress caused by the viscosity of a fluid flowing over a surface. It is defined as the ratio of the shear stress at the wall to the dynamic pressure of the free stream flow, Cf equal to tau W over 1 over 2 rho U squared, where rho is the fluid density and U is the free stream velocity. The objectives are: first, to comprehend flow physics through the analysis of features, including velocity profiles, boundary layer formations. Second, to verify theoretical answers like the Blasius solutions for laminar flows and assess the accuracy of the results by contrasting them with experimental data. Lastly, to compute critical flow parameters such as the skin friction coefficient, drag force, and boundary layer thickness.
Open the workspace, double-click the flow and save the object as flat plane. Right-click the geometry, select the new design model geometry. Now it's draw our rectangle. It's our flat plane. Give the dimension, where is our V1 and H2. As the data given, our H2 is 0.5 and the V1 is 1. Then go to modeling, create the XY plane, select the sketch 1, go to concept, find the surface from sketch, and create the sketch 1 and apply it. Then generate. Save the project, and close it. Double click the mesh, create the Z plane, then generate mesh. Now it's our rough mesh for the flat plane. Then go to the mesh, insert the face meshing, select the face, apply it, and generate. Well, it's still not much good, but the line now very straight. Go to mesh, insert the sizing. Use the edge pointer, select the top and bottom, apply it, and change the type of to number of division. The number of division is 15. Then generate. Go to the mesh again, insert the sizing. Now it's for the left size, apply it, and change the element size to number of division. Now the number of division is 16. And our base type need to change, and base factor is 17. Generate. Go to merge again. Now it's for the right side, insert the sizing. For the right side, apply it, and change to the number of division. Number of division is 16. And the bias type need to change. The bias factor is 17. Now need to apply the real bias. Click the right side again and apply. Generate. Now this is a good mesh for the flat plane. Then we use the surface pointer, select the surface, then right click, find the create name selection, name as airflow for the whole. Click OK. And use the edge. Select the left plane, create the name selection, name is inlet. Now it's the right edge, create the name selection, and name as outlet. And the bottom, right click, create name selection, as outline. For the top, right click, create name selection, name as far field pressure. Then click OK. Save the project again, and close it.
This is the setup process. First, we make a check to ensure the viscous is laminar. Then, we set up the materials of air. The density is 1 and the viscosity is 1 times 10 to the power of negative 4. After that, we set up the boundary conditions based on the value given in the equations. The velocity of inlet is 1.5 meter per second. Then we apply the symmetry type of far field pressure. Set up the method so that it is simple scheme. Set up the residual for continuity, x velocity and y velocity. After that, set up the initialization, make it standard, compute from inlet. Lastly, set up the calculation, then run it. Wait until it is complete. Then, this is the result we got.
Next is our result. This is the counter plot for velocity 1.5 meter per second and velocity 2.0 meter per second. The red region dominated the plot, indicating area with the highest velocity magnitude and reaching up to 1.66 meter per second for the velocity 1.5 meter per second, while reaching up to the 2.22 meter per second for the velocity 2.0 meter per second. This area suggests a uniform flow in most of the domain, likely corresponding to steady and fully developed flow condition. At the bottom edge, a gradient from blue to green visible represents the zone of lower velocity magnitude. This could be due to the presence of the boundary layer where the velocity transition from 0 to free stream velocity. Next is our velocity 1.5 meter per second chart. The velocity starts from 0, then increase to 1.5 meter per second. Y value we obtain from this graph is 1. This profile demonstrates the characteristics of laminar flow, where the velocity gradient is smooth and the graph and the flow layer move parallel to each other without missing. Next is the velocity 2.0. The velocity starts from 0, then increase to 2 meter per second. Y value we obtain from this graph is 1. The profile demonstrates the characteristics of laminar flow, where the velocity gradient is smooth and the flow layer move parallel to each other without missing. Next is result. The result for velocity is equal to 1.5 meter per second. The velocity starts from 0 meter per second, then increase to 1.5 meter per second. Y value we will obtain from this graph is 1. Since the y is equal to 1, the near wall flow in the viscous sublayer we have laminar. Next, the result for velocity is equal to 2 meter per second. The velocity starts from 0, then increase to 2 meter per second. Y value we obtain from this graph is 1. Since the y is equal to 1, the near wall flow in the viscous sublayer we have laminar.
On to relation between result and the theory. The first relationship is velocity. The flow speed up outside the boundary layer. This could happen if there's a pressure drop or a change in the flow geometry, like narrowing of the channel. Then, the boundary layer, thin layer of fluid near the surface, where the velocity changes from 0 at the wall to the free stream velocity. When the flow accelerates, the boundary layer becomes thinner because the flow speeds up near the surface. A thinner boundary layer means the velocity near the wall increases more quickly. And lastly, wall shear stress and skin friction coefficient. Wall shear stress is the force the fluid applies on the surface. As the flow accelerates and the boundary layer gets thinner, the velocity changes more sharply near the surface. This increases the wall shear stress, which leads to a higher skin friction coefficient. Okay, as you can see, this the effect of different airflow velocity of on the profile of the boundary layer form. So there are 4 parameters, which is the velocity profile, boundary layer thickness, transition to turbulence, and lastly the shear stress. As you can see, there is two states, which is the low free steam velocity and high free steam velocity. So that the gradual velocity changes, and at high free steam velocity, the steeper velocity gradient. But it's contrasts with the boundary layer thickness. At low free stream, the thicker laminar boundary layer, but the thinner laminar thicker turbulent at high free steam. The transition further downstream, while at high closer to the leading edge. The shear stress lower at low free steam and higher at high free steam. That's all from us. Thank you.